Hey everyone, thanks for tuning in and welcome to my talk. My name is Tom Barkley and I am the lab director at Trichome Analytical. Trichome is a third-party cannabis testing lab located in New Jersey. And the topic of my talk today has to do with standardization in cannabis pesticide testing, particularly the standardization of pesticide testing analytical methods. So today I'll be presenting a method that I've been developing to meet the AOAC standard method performance requirements. So pesticides, of course, refer to various different types of chemicals that are intended to prevent pests. The EPA definition is a little bit more broad and does include other things like plant regulators, defoliants, desiccants, and nitrogen stabilizers. Currently, the EPA has over 300 pesticide chemicals that are registered for use as pesticides. And currently, there are 59 pesticide products that are registered for use by the EPA specifically for hemp. And hemp, of course, is the only currently federally legal form of cannabis. And out of the 59 pesticide products, 58 have active ingredients that are considered to be biopesticides. And the one pesticide chemical listed as a conventional pesticide has an active ingredient of potassium salts of fatty acids. So these are all relatively non-toxic and relatively safe chemicals. And because of the legal status of cannabis in the United States, it is very much regulated on a state-by-state basis, with many of the states having their own programs and actual pesticide rules. So many times the states will divide up their cannabis programs based on either recreational, medical, and hemp. And hemp is also sometimes referred to as CBD or low THC. And I just wanted to highlight the medical cannabis market in particular and do a quick comparison of the different state pesticide testing rules and kind of highlight the issue that there is with the lack of harmonization between these states and their pesticide rules. So this chart is from a paper published last year in the Current Research in Toxicology. And in this study, they did a survey of the pesticide testing regulations in jurisdictions and states within the United States. And this is specifically for medical cannabis programs. And what they found is that there is a total of 98 insecticides that are regulated across the 21 of the surveyed jurisdictions in this study. But almost half of these were only regulated in a single jurisdiction out of the total number. So basically, what this means is that every state kind of has their own pesticide list for cannabis, and so there's definitely this lack of harmonization between states. And then also in the same study, they did look at the differences in action levels for the pesticides that were regulated by more than one state. And again, they found a pretty broad range of action limits. Some of these chemical pesticides you can see here range in having action levels from up to 3 orders of magnitude difference between the different programs, and that's represented here with these gray lines, with the median action level represented by the yellow circle in these charts. And the lack of standardization also exists for specifically for pesticide cannabis testing methods, analytical methods. And shown here are the results from an interlaboratory pesticide and cannabis proficiency test. So this is the 2021 Emerald test, which is specifically for pesticide in hemp flower. So for this test, each lab was supplied with a spiking solution containing the pesticides to be tested, as well as a blank hemp matrix material. And the labs were instructed to spike the pesticides directly into the hemp and then quantitate with their own methods that they utilize in each lab. And shown in this chart are the interlab percent relative standard deviations of the measured concentrations for each pesticide in this study. And these are listed based on their assigned concentration, which is shown at the top of the graph. And you can see that there is a fair amount of variability here. So approximately half of these pesticide analytes have a percent RSD that is greater than 30. And I think this probably can be attributed to the fact that each lab is pretty much running their own internally developed method, and there is no standard method being utilized for this type of analysis. And then also as the lab director at Trichome Analytical, I have to deal with pesticide testing pretty much every day at the lab. We test various different types of cannabis, hemp, which comes from different states throughout the country. We also test medical cannabis, which comes from in-state in New Jersey, the New Jersey Medical Cannabis Program. And we are also awaiting for the final testing regulations for New Jersey's recreational cannabis program. So there's definitely a lot to keep track of as far as the regulations. And, you know, there is a lot of complexity when it comes to multi-residue pesticide analysis. So we are definitely always looking for ways to try to simplify our methods and kind of harmonize the different testing methods that we utilize in our lab. So recently we were looking for ways to get involved in contributing towards the development of a standardized method for pesticides in cannabis. And there are a number of standards organizations that are getting more involved in cannabis, and one of those is AOAC. AOAC has a very active cannabis program called the Cannabis Analytical Science Program, or CASP. And in 2018, they published a standard method performance requirement for the quantitation of pesticides in dried cannabis materials. So the purpose of an SMPR in general is to serve as a guide for labs to submit possible methods for consideration as a standard method. And some of the highlights for the SMPR for pesticides in cannabis in particular is shown here. And there are a number of requirements such as the total number of pesticides to be tested for. In this case, there are 104. And within that list of 104 is pretty much any United States requirement for an individual state cannabis program, and that includes California and also Canada in that list. And there are a number of other requirements such as the percent recovery, repeatability, and reproducibility of the method. And then in addition, each pesticide has a recommended action limit and a limit of quantitation. So we basically wanted to see if we could develop a method that would meet all of these requirements in the AOAC SMPR. And so as a starting point for this project, I wanted to utilize our current in-house lab method for pesticides in cannabis. And that method, you know, we utilize both GCMS and LCMS. Those are both triple quad instruments. And we also use a single extraction step and a relatively simple cleanup process. For this project, we also were able to collaborate with Shimadzu Scientific and Millipore Sigma for their help in the method development process. So one of the first things that I wanted to explore with this method was the extraction solvent. And I had some prior experience working with one of the pesticides in the AOAC list, which is ethafon. And ethafon is not extracted very well using acetonitrile, so I wanted to try to use methanol. Methanol is commonly used in the lab, particularly for cannabis and extracting cannabinoids. And what I found was that methanol does actually work a lot better for extracting ethafon from hemp compared to acetonitrile. And the percent recovery that I measured for acetonitrile was around 10%, but with methanol it was around 90% for ethafon being extracted from hemp. And that's shown here in the bottom left of the slide. These are LCMS chromatograms. And you could also see here on the right side of this slide, these are superimposed chromatograms of ethafon extracted with various mixes of acetonitrile and methanol as the extraction solvent. And you can see that as the percentage of methanol increases from 100 or from 10% methanol in the black trace up to 100% methanol in the orange trace, that the peak response increases as well, which indicates the better extraction efficiency. Unfortunately, the problem with methanol is that it does appear to co-extract some of those more undesirable matrix components that can be problematic, such as chlorophyll. And you can see here on the left image, this is a comparison of just the visual color of the extract, acetonitrile versus methanol. You could see that the methanol extract has a much darker green color. And then even after the cleanup, which we're using a C18 solid phase extraction cartridge, even after that process, there's a lot of that green color left in the extract for the methanol extract. And so for these reasons and the difficulties with cleanup, for this method, I decided to stay with acetonitrile as the extraction solvent and not use methanol. So here is the sample preparation steps for this method. So the method uses a half a gram of cannabis weighed out into a centrifuge tube. 3 milliliters of acetonitrile is added, which is acidified with 1% acetic acid. After vortex mixing and centrifugation, the extract is cleaned up using a C18 solid phase extraction pass-through cartridge. The cartridge is then flushed additionally with 1 milliliter of acetonitrile, and that final diluted and cleaned extract can be analyzed directly by LCMS and GCMS. And then shown on the bottom left of this slide are the different steps at which the internal standard and the pesticide spiking solutions are added depending on the sample type. So for the spikes, the spiking solution containing the target pesticides as well as the internal standard are added directly to the cannabis before extraction, whereas for the calibration standards, the spiking solution and the internal standards are added during step 2 after the extraction solvent has been added. The calibration for this method utilizes an 8-point calibration curve. The standards are matrix matched, and a total of 87 of the pesticides are quantitated by LCMS, with the remaining 15 being quantitated by GCMS. Here are the instrument parameters for LCMS. The instrument that I used for this method development is a Shimadzu LCMS 8060 with electrospray ionization, operating in both positive and negative mode. The method here is a reverse phase method with a 2 microliter injection volume, and the initial mobile phase condition is 100% aqueous, and I found that helped with the elution of the polar pesticides in this method. For GCMS, I used a Shimadzu TQ8040NX. The injection volume was 2 microliters, and this is a splitless high pressure injection. So in order to test the method performance, I spiked the target pesticides in 3 different cannabis matrices. And I really wanted to see the difference in performance for these different types of cannabis. And those different types of cannabis are shown here. So I used a CBD biomass, which has a relatively low concentration of cannabinoids due to the fact that that's going to have some more leaves and stems mixed in with it. And then also I utilized a CBD flower and a THC flower. The cannabinoid concentrations are shown here. These were tested in-house with our cannabinoid potency method. The spiking solution level, or I should say the pesticide spiking level in the cannabis, was 100 nanograms per gram. And for those pesticides having limits of quantitation that were greater than 100 nanograms per gram, I spiked at 1 microgram per gram. And then also, the important thing to note here is that the blank material that was used to matrix match the calibration standards was the CBD biomass. So here are the spike recovery results for the first half of the LCMS pesticides. The second half is shown on the next slide. And these results are ordered by the retention time. So the earlier eluting pesticides are to the left, the later eluders are to the right. And the horizontal dotted lines represent the AOAC acceptable range for the percent recovery, and that's between 60 and 120%. And overall, you can see that the percent recovery for the CBD biomass is well within the acceptance limits, being between 60 and 120%. There were a few pesticides that are outside of the acceptance range for the CBD flower and the THC flower. And here are the results for the second half of the LCMS percent recovery data. So this is for the compounds that are eluting later in the run, between 5 minutes and 11 minutes. And there are a few interesting things going on with this data. The first is that the CBD biomass, again, is the recoveries there are well within the acceptance range. However, there are a number of results for the CBD and THC flowers that are outside of the acceptance range. And basically, my interpretation of this is that this is due to the matrix suppression and enhancement effects within the LCMS, which is going to be dependent on the actual strain. And I think this makes sense also given the fact that the non-polar co-extracted matrix components, such as the cannabinoids, are expected to be eluting in this part of the run, as opposed to the earlier part of the run, which was shown in the previous slide, where the percent recoveries were quite good for all 3 of the matrices. And then again, you can really see the difference between the CBD biomass, which was specifically used as the material to matrix match the calibration standards, compared to the results for those flower samples. And then moving on to the GCMS spike recovery results, you can see again that all of the tested analytes are within the acceptance range for the CBD biomass. Some of the later eluting pesticides, such as deltamethrin, cypermethrin, and cyfluthrin, had low, unacceptable results for the CBD flower and THC flower. So to summarize the performance of this method, there were 2 of the AOAC pesticides which could not be quantitated, and those were ethafon and aprodeon. So ethafon I mentioned earlier, that was an issue with the extraction solvent. Aprodeon I found to have a strong interference by both GCMS and LCMS. In this chromatogram on this slide, which is GCMS, you can see a comparison between the same level of aprodeon in acetonitrile versus in a matrix extract, and there is a significant interference there, which may be due to the cannabinoids. So out of the pesticides that could be quantitated with this method, there are a total of 102, and all of them met the percent recovery and repeatability requirements of the AOAC SMPR for the single spike level that was tested in this study. And the big caveat here is that the same batch of hemp or cannabis used for spiking also needed to be used for the matrix matched calibration standards. And then also for the AOAC recommended action limits or limits of quantitation, there were a total of 8 pesticides which could not meet the action limits that were specified by AOAC as specifically being action limits that were based on a survey of the regulations in the United States and Canada, which was part of that SMPR. The interesting thing about these 8 pesticides here is that they do, the performance of this method for the limits of quantitation for those pesticides does meet the action levels for various states that I've shown here, such as California, the New York Cannabinoid Hemp Program, and also New Jersey's interim testing standards. So you can see that the AOAC recommended limits are quite a bit lower from what I'm used to and what is commonly done for these states. So in conclusion, overall, I think that this method is definitely useful for labs wanting to quantitate a broad range of pesticides, meeting various state cannabis requirements. However, there were a few shortfalls in meeting all of the requirements of the AOAC SMPR. And the biggest issue in the method development was the low limits of quantitation for some of the pesticides, which were hard to meet. And basically, my focus in the method development, keeping these limits of quantitation in mind, was to try to increase the sensitivity of the method as much as possible. And the way that I approached that here was to not dilute the sample too much, which would effectively increase the amount of analyte that is being seen by the detector. And I think that that has definitely contributed towards some of the issues I saw with the matrix effects, differences between the different strains. One other thing that I should mention as well is that I did see some issues with the GCMS inlet getting dirty after repeated injections, and so I think that a further dilution could also benefit there as far as the GCMS repeatability. And overall, again, I think it's important for the industry moving forward to consider the fact that cannabis is a complex matrix. And as I've seen in this method development, what works for one type of strain might not work for another, especially when it comes to pesticide testing. and any potential future developments of a standardized method for pesticides in cannabis should keep this in consideration. So thank you very much for your attention. I'd like to again thank Shimadzu Scientific and Millipore Sigma for this help, for their help with this project. And please feel free to reach out to me at the email address listed here. Thank you very much.